Hello, my name is Sadat Farhad Khani, and I'm going to present our paper, Byzantine-Robust Federated Learning, which is a joint work with Youssef, Rashid, Nirupam, Rafael, Giovanni, and Sasha. In this paper, we study the impact of client subsampling and multiple local updates in the Byzantine Federated Learning setup. So let's start with federated learning. Federated learning is a recent machine learning paradigm where the goal is to train a machine learning model based on the data available to several clients, but without actually asking the clients to share their data. So we have a parameter server and n clients, and n actually can be a very, very large number. Each client has a local data set, and a loss function fi of theta can be defined on the local data set of client I. And the goal is to minimize a global loss function, which is simply the average of all local loss functions that we have for all clients. In our work, we do not assume this function fx to be convex, which means the goal of our optimization problem would be to find an epsilon critical point, which is simply any point for which the gradient is smaller than epsilon. And we have like some standard assumptions, which are like one of them is that these local loss functions should be Lipschitz smooth. And also the variance of the stochastic noise should be bounded by a parameter sigma, and the gradient dissimilarity or heterogeneity of the local losses should be bounded by another parameter, zeta squared. And these are like the assumptions that had been used in many previous works before this paper. The most well-known and actually the first algorithm for federated learning is called federated averaging, which is an iterative algorithm. At each iteration T of this algorithm, the server first selects a subset ST of clients, of n hat clients, where n hat could be potentially way smaller than n. So the server only selects a small number of clients in the system and broadcast the current global model to them. After that, each client that is selected performs k local gradient steps and computes an update vector and sends this update vector UTI to the server. And then the server computes the average of these update vectors and updates the global model and moves to the next round to T+1. Federated averaging is a very well-studied algorithm, and it's been studied by a lot of papers before, and it works well when everything is good in the system and all the clients perform exactly what they're supposed to do. But in a real-life scenario, especially when we don't have control over all the clients that we have in the system, we should expect actually some of them to misbehave for various reasons. For instance, some of them might crash, or some of them might have low quality or poisonous data. And because of that, they might actually send update vectors to the server that are not desirable. To like encompass all these bad things that could happen to the system, the Byzantine threat model has been introduced and studied before, where we assume that some of the clients in the system might be what's called Byzantine. And it means that they basically can send any arbitrary vector to the server instead of like a genuine update vector that is computed on the data. So in our work, we assume up to B clients in the system could be Byzantine, and this B is a parameter which is known. And B cannot, of course, be more than half of the clients in the system. Okay, now that we have the Byzantine clients in the system, the federated averaging algorithm might actually fail to converge, and the reason is simple. It's because if a client is Byzantine and it's selected by the server, then this client can actually send any arbitrary vector with any magnitude to the server, and then the server just computes the average of this Byzantine vector with several like honest vectors. But the output of the average can also be like arbitrarily manipulated. So it means that the federated averaging algorithm might actually not converge. To solve this issue, it's been proposed by several previous works to replace the averaging operation at the server with a robust aggregation function or a robust averaging function. For instance, the median or team mean, and there is like a long list of different aggregation functions that we can use that has been studied by like different previous works. But most of these previous works usually make two simplifying assumptions in their analysis. One is that there is no client subsampling, which means that in all learning iterations, the server just selects all the clients in the system. And the other simplifying assumption is that each client can actually take one single local gradient step and not multiple ones. So in our work, we try to understand what happens in the general case when we do have client subsampling and each client is allowed to take multiple local updates. And our main result is this theorem that you can see here, which is basically a convergence guarantee for federated robust averaging. So what this theorem says is that if the sample size is large enough, and in particular, if it's larger than the quantity that grows logarithmically with the number of learning iterations, then you get this nice convergence rate that you can see here. So in this convergence rate, the first three terms are the standard terms that you would get for federated averaging and without any Byzantine client. And the last term is the term that is caused by the Byzantine clients, and I call this term the asymptotic error. You can find discussions in more details about the theorem in the paper, but in the rest of this presentation, I'm going to talk about several implications of this theorem regarding client subsampling and local updates. So regarding client subsampling, the first message that we have is that in order to guarantee convergence, we need the sample size to be greater than a threshold value, which depends on the number of learning iterations in a logarithmic way. And the reason is that if the sample size is very small, then with non-negligible probability, we are going to get a majority of Byzantine clients in some iterations, and it means that in those iterations, the Byzantine clients will get full control over the output of the aggregation function. And in order to prevent this, we need to assume that the sample size is actually larger than this quantity here. And you can also see this in the plot below, where when the sample size is small, the algorithm does not converge. And when we increase the sample size at some point, we start to see the convergence of the algorithm. So the second important message that we have in the paper is that if you keep increasing the sample size further away from the threshold value that we just discussed, it's going to improve the convergence guarantee, which is expected, but this improvement is going to saturate quite early, which means that there is another threshold value, which is called n hat opt here. And when you reach this value, you actually get order optimum convergence guarantees, which means that increasing the sample size after this point actually does not give you any improvement in terms of the rate of convergence. And we call actually this phenomenon the diminishing return in the paper. And finally, about multiple local updates, what we learn is that if you tune the step sizes properly, increasing the number of local updates actually improves the convergence guarantee that we have. And the reason is that each update vector that we get from a client is roughly the average of k stochastic gradient, which means that the variance of the update should actually decrease by a factor of k if the local step size is small enough. And we actually formalize this in our proof in the paper. And yes, this concludes my presentation. You can find the URL of the paper with this QR code here. And thank you for your attention.